Welcome to G Fun Facts Online. The universe is a symphony of motion, but not all dancers are equal. Most celestial bodies move to the gentle, predictable waltz of Newtonian physics, their orbits governed by the mild curvature of space-time. But in the deepest, darkest corners of the cosmos, the dance becomes chaotic, relativistic, and profoundly extreme. At the absolute pinnacle of astrophysical obsession lies a theoretical pairing so perfect, so uniquely suited to testing the very limits of human knowledge, that astronomers have spent more than half a century searching for it. They seek the ultimate cosmic laboratory, a rapidly spinning neutron star known as a pulsar, locked in a relentless gravitational embrace with a black hole. To understand why this specific binary system is considered the Holy Grail of modern astronomy, we must first dive into the nature of the two distinct entities involved. They represent the extreme endpoints of stellar evolution, the crushed remnants of massive stars that have exhausted their nuclear fuel and collapsed under their own terrifying weight. Yet, their natures could not be more different. One is the universe's most perfect clock. The other is its darkest abyss. When the ultimate metronome meets the ultimate shadow, the resulting ripples in spacetime hold the power to either confirm Albert Einstein's general theory of relativity in its most extreme regime, or to break it entirely, paving the way for a brand new era of physics. Let us begin with the anatomy of a metronome. The story of the pulsar begins with the violent, spectacular death of a giant star. Picture a star with a mass roughly 8 to 20 times that of our own Sun. For millions of years, it sustains itself through nuclear fusion, pushing outward against the crushing inward force of its own gravity. But eventually, the fuel runs out. The outward pressure drops, and gravity wins the ultimate wrestling match. The core collapses in a fraction of a second, rebounding in a cataclysmic supernova explosion that outshines entire galaxies. What remains in the aftermath is a neutron star, a sphere of incredibly dense matter, roughly 20 kilometers across, which is about the size of a large city, yet containing more mass than our entire Sun. The density is so extreme that protons and electrons are violently crushed together to form a highly compressed fluid of neutrons. To put this into perspective, a single teaspoon of neutron star material would weigh billions of tons on Earth. Because of the conservation of angular momentum, the same physical principle that causes a spinning figure skater to rotate faster when they pull their arms in, this collapsed core spins at a staggering rate. Furthermore, the dying star's magnetic field is incredibly compressed, creating a magnetosphere trillions of times stronger than Earth's. As the newly born neutron star spins, this intense magnetic field rips charged particles from the surface and accelerates them to near the speed of light, beaming highly focused electromagnetic radiation out from its magnetic poles. If the star's magnetic axis is misaligned with its axis of rotation, these massive beams of radiation sweep through space like the light from a frantic cosmic lighthouse. When one of these beams sweeps across Earth, our radio telescopes detect a brief, sharp pulse of radio waves. Hence, the term pulsar. The discovery of these bizarre objects is one of the most famous and fascinating tales in 20th century astronomy. Back in 1967, Jocelyn Bell, a 24-year-old postgraduate student at the University of Cambridge, was analyzing miles and miles of paper chart recordings from a newly constructed radio telescope. Poring over the data by hand, she noticed a bit of scruff, a strange repeating signal pulsing precisely every 1.33 seconds. The signal was so unnervingly regular, so perfectly timed, that for a brief period, Bell and her supervisor, Anthony Hewish, jokingly dubbed it LGM-1, which stood for Little Green Men. They legitimately wondered if it might be an extraterrestrial beacon. It was soon realized, however, that they had not found aliens, but rather the first rapidly rotating neutron star. This discovery fundamentally changed astrophysics, eventually earning the 1974 Nobel Prize in Physics. Though awarded to Hewish and Martin Ryle, Bell Burnell's exclusion from the prize remains one of the most controversial decisions in Nobel history. Over the decades, astronomers found even more extreme versions of these objects known as millisecond pulsars. These pulsars have been spun up over millions of years by siphoning matter from a companion star, reaching mind-bending rotational speeds of hundreds of times per second. Because of their massive inertia, millisecond pulsars are incredibly stable rotators. The arrival times of their pulses can be predicted to an accuracy of a fraction of a microsecond. making them cosmic clocks that rival, and sometimes even surpass, the precision of the very best atomic clocks on Earth. Now, if the pulsar is the ultimate clock, the black hole is the ultimate devourer. When a star significantly more massive than the Sun dies, not even the quantum mechanical repulsion of neutrons, known as neutron degeneracy pressure, can halt the gravitational collapse. The core shrinks endlessly until it breaches its own Schwarzschild radius, forming a black hole, a region of space-time where gravity is so intense that nothing, not even light itself, can ever escape. Black holes are entirely characterized by just three properties: mass, spin, and electric charge. This is famously known as the no-hair theorem. Despite this apparent mathematical simplicity, they warp the fabric of space-time in ways that completely defy everyday human intuition. Around a black hole, the gravitational pull is so severe that it causes time to drastically slow down relative to a distant observer, a mind-bending phenomenon known as gravitational time dilation. Furthermore, if the black hole is spinning, it literally drags the fabric of space and time around with it, much like a spoon stirring thick honey. This effect is known as frame dragging, or the lens-thirring effect. For decades, black holes were mathematically fascinating, but observationally elusive. We can only see them by observing their effects on their immediate surroundings, whether by watching stars whip around an invisible center of mass at terrifying speeds, as they do at the core of our Milky Way, or by detecting the high-energy X-rays emitted by superheated gas spiraling helplessly into the void. So, why do astrophysicists want to put these two extreme objects together? They love pulsars because their clock-like precision makes them perfect probes for the fabric of space-time. By carefully measuring the time of arrival of a pulsar's ticks, astronomers can detect minuscule changes in its environment. If a pulsar is moving toward us, the pulses arrive slightly closer together, which is a blue shift. If it is moving away, they arrive further apart, which is a red shift. This technique, known as pulsar timing, has already yielded some of the most rigorous tests of general relativity in history. In 1974, Russell Hulse and Joseph Taylor discovered the first binary pulsar, a neutron star orbiting another neutron star. By timing the pulsar over several years, they observed that the orbit was slowly, imperceptibly shrinking. The system was losing energy at the exact rate predicted by Einstein's theory due to the emission of gravitational waves, which are actual ripples in space-time radiating outward from the orbiting masses. This monumental discovery earned Hulse and Taylor the 1993 Nobel Prize in Physics. Later, in 2003, astronomers at the Parkes Observatory in Australia discovered the first double pulsar system, where both neutron stars are actively emitting beams that sweep across Earth. With an incredibly tight orbital period of just 2.4 hours, this system allowed astronomers to measure relativistic effects to a staggering 99.99% accuracy. They even measured the Shapiro delay, which is the subtle slowing of light as it struggles to climb out of the gravitational well of the companion star. But as profound as the double pulsar is, it still involves two relatively lightweight objects. The gravitational fields, while strong, are not the absolute maximum the universe can offer. To push general relativity to its absolute breaking point, and to test alternative theories of gravity like scalar tensor gravity, astronomers need a pulsar orbiting a black hole. If a millisecond pulsar were orbiting a black hole, its highly regular ticks would be subjected to the ultimate funhouse mirror of spacetime. As the pulsar swings close to the black hole, the immense gravity would cause the pulses to arrive progressively later, an effect known as the Einstein delay. The light itself would be bent and stretched. The black hole's frame dragging would cause the pulsar's orbit to precess, or wobble in highly complex ways. By measuring these timing anomalies, astronomers could weigh the black hole with unprecedented accuracy, map its exact spin, and rigorously test whether the no-hair theorem truly holds up under scrutiny. Furthermore, any deviation from Einstein's predictions would be the first tangible crack in general relativity, a vital clue in the long-sought quest to unite gravity with quantum mechanics. Given all of this, and considering the billions of stars in the Milky Way, why has a pulsar black hole binary been so difficult to find? The answer lies in the incredibly messy, violent reality of stellar evolution. For a pulsar and a black hole to end up in a binary orbit, they must begin as two highly massive stars locked together in a binary system. The heavier star will run out of fuel first, exploding in a supernova and collapsing into a black hole. This explosion must not be so violent that it breaks the gravitational bond between the two, an event known as a supernova kick. Millions of years later, the second star explodes, collapsing into a neutron star. Once again, the fragile system must survive the kick without flying apart. Even if the binary amazingly survives both cataclysmic explosions, a secondary issue arises, known as the swallowing problem. If the orbit is too tight, or if the black hole is too massive, the black hole's tidal forces will simply rip the neutron star apart and swallow it whole, extinguishing the pulsar forever. Conversely, if the orbit is too wide, the relativistic effects are far too weak to be measured with the necessary precision. Furthermore, searching for pulsars requires looking through the dense gas, plasma, and dust of the Milky Way galaxy. Free electrons in interstellar space disperse radio waves, causing the sharp, distinct pulses to smear out into an unreadable mess. This makes finding fast-spinning millisecond pulsars incredibly difficult, particularly in the galactic center, where black holes are most abundant. For decades, astronomers have scoured the skies with the world's largest radio telescopes, finding thousands of pulsars, but the elusive black hole companion remained deeply hidden. That was until the 2020s brought the dawn of next-generation arrays. The first major breakthrough in this quest occurred in January 2024, utilizing the spectacular capabilities of the Meerkat radio telescope in South Africa. An international team of astronomers targeted a globular cluster named NGC 1851. Globular clusters are ancient, densely packed spheres containing hundreds of thousands of stars. They are essentially the cosmic equivalent of a heavy metal mosh pit. In these impossibly crowded environments, the normal rules of stellar evolution are frequently interrupted by dynamic encounters. Stars pass so close to one another that they can disrupt orbits, swap companions, or even collide head-on. It is a prime hunting ground for exotic binaries. In NGC 1851, the team analyzed the ticks of a millisecond pulsar, rotating over 170 times per second. It resides in an eccentric 7-day orbit with a massive dark companion. By precisely measuring the orbital motion via pulsar timing, they calculated the total mass of the system and isolated the mass of the companion object. The result was absolutely stunning. The dark companion weighed in at approximately 2.35 times the mass of the Sun. This specific number falls precisely into what astrophysicists call the black hole mass gap. According to established theories of stellar collapse, the heaviest a neutron star can get before its own gravity overcomes neutron degeneracy pressure and crushes it into a black hole is about 2.2 solar masses. Meanwhile, the lightest black holes formed from collapsing stars are generally observed to be around 5 solar masses. The companion to this pulsar sits right in the middle of this forbidden zone. Is it the most massive neutron star ever discovered, defying our understanding of nuclear physics at extreme densities? Or is it the lightest black hole ever found, challenging our models of stellar collapse? Astronomers theorize that this mass gap object may not have formed from the collapse of a single star. Instead, in the chaotic environment of the globular cluster, 2 smaller neutron stars might have collided and merged, forming a single, bloated, supermassive object. This new arrival then wandered through the cluster, gravitationally kicking a white dwarf out of its orbit and capturing the millisecond pulsar for itself. Regardless of whether it is an unimaginably heavy neutron star or a lightweight black hole, this discovery proved that the long-sought extreme binaries exist, providing a unique laboratory for probing matter under the universe's most brutal conditions. But while the mass gap binary provided a tantalizing glimpse into extreme stellar physics, it left the ultimate test of general relativity somewhat ambiguous. Astronomers still hungered for an undeniable, confirmed black hole, and ideally, the biggest one of them all. In February 2026, the astrophysics community was electrified by a report from the Breakthrough Listen Galactic Center survey. A team of scientists utilized some of the most sensitive radio investigations ever conducted to scan the incredibly turbulent central region of our own Milky Way. At the heart of our galaxy lies Sagittarius A star, a supermassive black hole weighing 4 million times the mass of the Sun. Surrounding it is a chaotic maelstrom of orbiting stars, superheated plasma, and dense magnetic fields. The sheer amount of scattering and dispersion caused by the plasma makes detecting the crisp radio ticks of a pulsar near the galactic center an incredibly daunting task. Despite these overwhelming odds, the researchers identified a highly promising signal, an 8.19 millisecond pulsar candidate located in the immediate vicinity of the supermassive black hole. The implications of this potential discovery are staggering. If follow-up observations confirm the pulsar and astronomers can successfully map its timing residuals, it will represent the Holy Grail of observational relativity. Tracking a fast-spinning pulsar in the intense gravitational well of a supermassive black hole would allow scientists to directly measure the distortion of spacetime on a macroscopic scale. A confirmed millisecond pulsar orbiting Sagittarius A star would essentially act as an ultra-precise GPS satellite charting the extreme curvature of the black hole's event horizon. It would allow physicists to measure the exact spin of the supermassive black hole and potentially observe the effects of quantum gravity, probing regions where our current understanding of physics completely breaks down. As we stand in the late 2020s, the search for galactic metronomes in the shadows of black holes has transitioned from a theoretical dream to an awe-inspiring observational reality. These massive breakthroughs were made possible by the meticulous preservation of legacy data and the rapid advancement of telescope arrays. Looking forward, the imminent completion of the Square Kilometre Array in Australia and South Africa, alongside the next-generation Very Large Array in North America, will increase our sensitivity by orders of magnitude. The Square Kilometre Array is projected to be so unbelievably powerful that it will likely detect every single observable pulsar in the Milky Way that is beamed toward Earth. Within that vast, unprecedented catalog, astronomers anticipate finding dozens of pulsar black hole binaries representing various masses and orbital configurations. Each new binary discovered will act as a cosmic tuning fork struck against the very fabric of the universe. By listening to the precise, unyielding rhythm of their pulses, humanity is learning to read the deepest secrets of gravity. We are moving beyond the elegant equations scribbled on chalkboards a century ago, stepping into the cosmic laboratories, where space-time itself is warped, dragged, and torn apart. The dance between the pulsar and the black hole is a silent one, playing out over millions of years across thousands of light-years of cold, empty space. But through the giant metallic dishes resting on the surface of our pale blue dot, we have finally learned to hear the music. And as the ticks of the metronome continue to echo out of the abyss, they promise to reveal the ultimate truths of the cosmos, how it began, how it works, and how, inevitably, it will end. Thank you for joining us today on G Fun Facts Online. Keep looking up and stay curious.